you can see on screen a summary of the project itself, which was funded by Innovate UK under the SBIR ZE road freight competition rules. And it enabled DAF UK to place 20 of our Phase 2 electric LF vehicles, which were 19-tonne rigids, into the NHS supply chain and local authorities. And this project now has been running for 18 months, and we'll go into some of the key learnings and the results when Tom and Chapper come up. So from a project partner perspective, it was Innovate UK that provided the funding for the vehicles, the charging infrastructure, and all of the monitoring equipment, tools and software. And we've been having regular review meetings throughout the project. We then have DAF and Leyland Trucks, and we were responsible for manufacturing the vehicles, procuring the charging hardware and software, and delivering the vehicles into the fleets, including the driver training that was required for the end users. And the data collection was subcontracted to Cenex, who you'll hear from shortly. And Cenex provided the systems and tools to capture and analyse the data, both from the vehicle, the driver, and from the charging infrastructure. And we can see some deep dive reports that have been produced periodically throughout the project, which you'll hear about today.
So collectively over the trial, we have seen that the trucks have covered about 287,000 kilometres of distance, which is roughly about 2/3 of the way to the moon from the Earth, rather astronomical. And the trucks have used 275,000 kilowatt hours worth of energy, which is the amount of energy to make enough tea to fill 1 1/4 Olympic swimming pools, lots of tea. And we've also found that we've saved 210 tonnes of carbon dioxide over the course of the trial. So, alongside the trial monitoring, we've also done some deep dives where we look into the data, the trucks and their operation, their energy consumptions, as part of deeper insights, which we published onto the BETT website. I'll take you through a quick whiz through them, like a highlight reel of them. If you want more information on these deep dives, they're all available on the website where you can look at the findings and the data in detail. So if we look at drive cycle efficiency and regeneration, just a couple of points to cover here. Drive cycle refers to the type of driving that the vehicles did rather than the classification of the roads they're on. So we split them into 3. We have rural, urban and motorway. Urban refers to driving which has lots of starts and stops, which you usually see in cities and busier areas. Motorway driving has more constant speeds and less braking, and rural is somewhere in between. Regeneration refers to the ability of the vehicles to use kinetic energy from braking to feed that energy back into the battery to be used again. So this first graph here shows that with urban driving, you can regain about 25% of the energy by braking. So for every 100 kilowatt hours used, you can gain back 25 kilowatt hours of energy back into the battery to use again. This next graph shows the drive cycles with the range on the top and the efficiency at the bottom. The clearer parts on the top of the bars that you see there show how the range and efficiency can be extended via the use of regeneration. So this is a graph showing the overall efficiency of all the vehicles and their range. We found that the efficiency of all the vehicles is about 1.1 kilometers per kilowatt hour and a range of around 270 kilometers, which is roughly around the range that DAF was expecting. So it's good that these vehicles are meeting their expectations. Just as a note, about 8 vehicles out of the 20 have a temperature controlled unit. It is labeled as refrigerated here. And you can see that in this graph, the vehicles with the temperature controlled unit has slightly lower efficiency than the normal vehicles. Initially, you may think that this decrease in efficiency is due to some of the power being consumed for the temperature controlled unit rather than propulsion of the vehicle. But if you look at the data behind the scenes, this actually is not the case. So we'll look at some of the things that affect efficiency of the vehicle, such as payload, the weather and ancillaries, and we can see exactly why the vehicles with the temperature controlled units have a slightly lower efficiency. So if we look at the relationship between payload and efficiency, this graph here is split by the 3 drive cycles. You can see that generally there is a drop in efficiency as payload increases, which makes sense. Heavier vehicles require more energy to move off and do their journeys. So just taking into account everything that we talked about, so outside temperature, use of ancillaries and payload, the most likely reason behind the decrease in efficiency of the temperature-controlled vehicles compared to the normal vehicles is most likely due to the increased mass, because the unladen weight is about 2 tons heavier than normal vehicles, and they generally carry a ton extra weight during their journeys. From these insights, I think one of the main takeaways is that the effects of payload, temperature, and ancillaries on efficiency are quite useful for fleets, just so that they understand what they can expect in terms of truck performance under various conditions.
So we asked all of the drivers, both at the beginning of the trial and at the end of the trial, what their expectations were and what their experiences were of driving an electric truck compared to the diesel vehicle they normally drive. We asked them a number of questions, including questions about acceleration, performance, manoeuvrability, range, and such like. And you can see from these results, for almost all of the questions, the drivers rated the electric vehicle either better or much better than the diesel equivalent. There are obviously a couple of answers where the result was a little bit less favourable, the obvious one being the range on a full charge, although we never expected an electric vehicle at this stage to have quite the range of a diesel vehicle, so that is an expected result. If I add a few more lines to the diagram, this shows how those opinions changed throughout the trial. So you can see that for some, such as acceleration, the answers that the drivers were giving at the end of the trial compared to what their expectations were at the beginning are actually quite significantly better. And that is also true for the majority of the answers, showing that once the drivers get into the vehicles, they actually have a better opinion of them than they did even beforehand. This is actually really important, because if the drivers don't like the vehicles, it's going to be really hard to adopt them onto fleets. So this really shows that the idea of the drivers not liking the vehicles is a complete myth. Drivers tend to really love the vehicles, and that just shows that that isn't going to be a barrier to adoption of the vehicles on fleets in the future. The only one that is a little bit negative is truck reliability. However, the vehicle is in operation with fairly early versions, and there's always going to be some niggling, teething issues, which will likely resolve themselves over the course of further development of these vehicles. So, moving on to the fleet managers, we did interviews with all of them and asked them what the drivers thought and what their experiences were with the vehicles. So the first quote I have here is actually one that nearly every single operator told us, which is that the drivers love to drive the vehicles. And this reflects the answers that we got to from the drivers, which I showed on the slide before. And as I say, it's very important that the drivers like the vehicles, and indeed they do. One slightly unintended consequence of a vehicle that doesn't make any noise is it meant that some fleets were able to deliver to places that they couldn't do in a diesel vehicle. Certain places don't like it when you're driving loud diesel vehicles nearby, and this just opened up the possibility of being more flexible with when the vehicles were being operated. Again, going back to the theme of the driver's experience of driving the vehicles, the fact that they're so much easier to drive, there's no gears, the power delivery is smooth and the manoeuvrability is good, were some of the more specific reasons why the drivers said they like driving the vehicles. And it goes like a rocket. Again, drivers tend to like driving something that's more powerful than something that's just dawdling along, and they really appreciated the immediacy of the power you get from an electric motor. And also, the electric trucks attracted attention and they're great for marketing, which is really good for fleets that want to portray their green credentials. Having an electric truck on the road, and particularly when it's liveried up with the fact that it's an electric truck, is a really great marketing opportunity and shows that these organisations are trying to do something better for the environment. Of course, it's not always good, and there were some more negative comments. So one that we had was that the cab was quite hard to keep warm, which did negatively affect range. And actually our analysis showed that although it had quite a modest effect on range, clearly when you have a more limited range than a diesel vehicle, it is important to be as optimal as you can. And of course, the drivers really want the cab to be warm in the winter. So this is a potential area for development in future versions of the vehicle. Also, they'd like to go further, but they need somewhere to charge en route. All of our operators were using depot-based charging, and that's because it's very difficult to charge a heavy goods vehicle on the public charging network at the moment, mainly due to the physical size of the trucks not being able to get to chargers which are predominantly designed for cars. So this shows the importance of charging infrastructure on being able to extend the range of the vehicles, which in turn means it'll be much easier to adopt these vehicles into a fleet. And also, the vehicles were great. We were only let down by the chargers. And this reflects the fact that when there were technical issues, they tended to be more with the chargers than the vehicles. And some of that was not just physical charger, but it might have been the communication or the back end of the chargers that was not working properly. But it does really demonstrate the importance of having fully functional chargers in order to make sure the uptime of the vehicles is what the fleets need to be able to rely on them. Of course, if you can't charge a vehicle, you can't drive the vehicle. So it's just as important as the reliability of the vehicles themselves. And also, technical issues, when they did happen with the vehicles, did take longer to resolve than they were used to with diesel vehicles. But this was partly due to a smaller number of technicians which were able to work on electric vehicles. But this is a problem which is likely to start resolving itself once electric vehicles become more common and there are more trained mechanics to deal with those issues. And finally, I've put another comment that was very specific that came from a lot of vehicles, and it's that the relatively early version of the truck that the drivers were using had an analog state of charge gauge, which was actually quite difficult to read, and it made it difficult for the driver to understand how much range was left in the vehicle. And this contributed to some issues of range anxiety. Although range anxiety wasn't a major issue that was seen during the trial, having good information in the cab about how far the vehicle can go is really useful and does mean a driver can get the most out of the vehicle and be comfortable they can take it home. Now, it's good to say that the latest version of the vehicle from DRAF has a far improved dashboard which shows this information a lot more clearly, but I wanted to put this here because this will have coloured some of the results that the drivers gave to us and might explain some of the slightly negative comments around the range and reliability of the vehicle. Moving on, the graph on the left-hand side here shows the total carbon emissions over the lifetime of a vehicle. The first thing to note is the grey part of the bar, which is the use phase emissions, dwarfs in most situations the production phase, which means that even though the production emissions are a lot greater for battery electric vehicles due to that battery, because of the much lower emissions during the use phase, because of the cleaner electricity grid in the UK and Denmark, those emissions are reduced by about 40% and 70% respectively. Of course, if you have a dirty grid, you feed dirty electricity into your truck, those carbon emissions do go up, which again just shows how important the source of your electricity is for the overall carbon emissions. Now, in our example here, we're using a typical 50,000 kilometre range for a truck such as this, and if you operate your truck like that, then you actually have a carbon payback of somewhere around a year compared to a diesel equivalent, providing you're using a UK or Danish grid mix. The BETT vehicles haven't gone quite 50,000 kilometres per year, but this shows that even with lower mileage per year, the payback is still within the 7-year lifetime of the vehicle. So that's everything from me. I just want to say that there's much more detailed information on the BETT website, so please visit that and you can look at many of the reports we've published to get far more detailed information.